this computer. Well, good afternoon, and also good morning for some folks in Europe and China. And my name is Wenming Yi, and I also have Joe Eaton here. So we've been running this workshop for quite a while, and would like to kind of also introduce some of the other members as well. So Xiao Yun has been also helping out with the workshop, and she'll be giving a talk. And Rick here from Nvidia also, so he'll be also be part of the talk. So we have a couple of announcements. So first of all, I think as COVID is kind of receding a little bit, we're thinking about potentially running a maybe in-person kind of a DGL workshop at some point, thinking about the Bay Area. So if people are interested, certainly reach out to us, and we would like to maybe run something like that in September or October timeframe. So if folks would like to do that. The second announcement is we have just released DGL 0.9. If you have any kind of feedback and thoughts, please do reach out to the DGL team on the Slack channel. And our Slack channel has grown to be about 1,400 users. So we're really excited to see the community growing. And also we're potentially thinking about running, this workshop. If we have content, we've missed a few workshops, these user group meetings this year because we didn't have enough content. Also, the organizers got a little busy, and I'm probably 95% guilty of it. So I would say, if we have content, we would like to continue to run it once a month. And if we don't, we might skip a month. But also, I'm looking for volunteers to help organize this. I think there's definitely a lot of people that are interested in attending. And the second thing is that there are we're also thinking about potentially running this in Europe. If there are folks that would like to organize like a sub user group in Europe, we would love to work with you. So we certainly have a lot of interest in Europe. I know a lot of folks are actually calling in very is it very early? Is it like 2 o'clock in the morning by now? I don't know what the what is the time in Europe right now. It's like 2 o'clock in the morning. So so we might consider having consider having a different time. So Joe, I'd love to see if you have any announcements or anything you'd like to.
One question I've got is, do you have a location picked out for the proposed Bay Area? Would it be in an office somewhere or some university?
So we're thinking about the Bay Area, and we have offices here. We have really nice offices here in Palo Alto, or even close to Santa Clara. And I'm thinking, if you guys, if Nvidia, which is like you guys are literally within walking distance to where we are.
Yeah.
So well, I mean, everybody is. I mean, Intel.
Yeah, we could alternate locations.
Yeah. So
it's all
everybody is.
In a small area.
Yeah, it's a small area. So I mean, that's what we call Silicon Valley, right? So I mean, we can probably host it in Nvidia. That's another possibility. But I think definitely we're thinking about gathering a few folks together. And I know Joe, you're in Austin, so that's not that convenient. But Xiao Yun is here in the Bay Area. Any other questions or thoughts that you have? And also, if folks on the phone would like to chat.
Yeah, just a call out to everyone. If you have some interesting work in GNNs, let us know. We'll try to get you in the schedule. And we're also looking for interns, looking for people interested in working on GNNs for a PhD or as research. We're looking for interns to push the field forward.
Yeah. Oh, that's great. And I know a lot of folks, a lot of, students especially, and folks who are looking for new jobs. The industry, tech industry is very strong. But at the same time, we do have, potentially a recession, and a lot of companies kind of are having a hiring freeze. Amazon is not having a hiring freeze. So we also do have some positions related to graph neural network. I'm not going to advertise. I know some of our folks like Song Shang, who is on this call, and he has positions open, and he can provide you with more details. So you might want to reach out to Song Shang directly if you're, looking for a job. And also, Joe has position opportunities in Nvidia. So do definitely reach out to us, and we can help you if you're incoming graduates or in other situations where you're looking for a new position. So with that, I'd like to maybe introduce our first speaker, who is already on video. So Peiqi Ying is going to talk to us about DGI, and I have to be very careful how to read it because there's DGL, and I have another project called DJL, so it's all very confusing. So DGI, automatic GNN inference on large graphs, and Peiqi is from Southern University of Science and Technology in Shenzhen. So Peiqi, please go ahead and share your slides, and we'll get started.
I think you're on mute, Peiqi.
Mute.
There we go. There we go.
Yeah, you're on mute. So you're still on mute.
Hi, can anybody hear me?
Now we can.
Okay. And my title is DGI, Automatic Gen Inference on Large Graphs. This work is joint work with Dr. Mingjie Wang at AWS, Professor Xiao Yun, and Professor James Cheng. And let me just first introduce myself. I'm previously an undergraduate student at SUSTech, and currently I am a first-year PhD student at COHK, and I'm a research intern in AWS Shanghai AI Lab and working on the DGL program. And this is the content of my talk today. And I will first introduce the background and talk about our general ideas and the system design. And finally is the optimizations, evaluations, and conclusions. The graph data are ubiquitous, such as social network, knowledge representation, and bioinformatics. These are really important in the graph application. And graph neural network achieve outstanding performance on many tasks, such as node classification and clustering and link prediction. And many different many GNN models with different structure has been proposed, like GCN, Graph Convolution Network, GAT, Graph Attention, GNNs, the Jumping Knowledge Network, and APPNP. And most of them try to scale K layers to compute embedding, and they aggregate their neighbors to compute the next layers embeddings, mostly like this, and I think everybody's noticed. And this will pose an issue called the neighbor explosion, and those will go implosionally with the increase of the number of layers. For example, this is the target node and these three nodes are the one layer neighbors, and these are the second layer's neighbor. And the outside circle is the third layer neighbors. And it's obviously with the increase of the layers, the nodes will go explosionally. And to avoid this, many previous work has been proposed, such as GraphSage. It just sample the neighbors, and like GraphSaint, it limit the model calculation to a subgraph, which is also known as subgraph sampling. And like GNN Autoscale, it used historical embedding to compute the aggregation. But unlike training, GNN inference requires all their neighbor to make an accuracy prediction of a node, which means we have to fetch all their k-hops neighbors and could not use the methods of sampling. And this is the timeline of the GNN inference. It will just start with select a batch of nodes and then fetch all their k-hop neighbors and their features. And then we compute the embeddings. And this time we annotate it as the node-wise inference. But node-wise inference suffers from the repeated computation. And since it grows proportionally with the number of layers, listen for GCN, JT, GraphSync, and GraphSend, with the increase of the layer, the infer time domain the total time compared to training. And to accelerate GNN inference, DGL proposed an layer-wise inference approach, which they used all their feature to all their embedding to compute the next layer's embedding. And after all the tensors, after all nodes have been computed, they will use this layer's embeddings to compute the next layer embeddings. And this is the layer-wise inference workflow. It will first enumerate each GNN layers and then create an empty tensor for the output tensors. And then it selects a batch of nodes and fetch all their one-hop neighbors and features, and then compute embeddings and finally record result in the output tensor. Compared to the node-wise, it just have this step more than the node-wise approach. And this is the comparison between the node-wise inference and layer-wise. For example, this is a graph, and the node-wise to compute the batch A and B. For node-wise approach, we will first use FE to compute C, to use GH to compute D, and then use CD to compute A. And for another batch, it will first use FE to compute C, use GH to compute D, and use CD to compute B. And it's obviously the computation of C and D are repeated. But for the layer-wise inference, we will first use the FE to compute C, to use GH to compute D, and then we use CD to compute A, and then use CD to compute B. And layer-wise inference can avoid the problem of repeated computation. But there's a very big drawback of layer-wise inference. It's complex implementation. Since node-wise can reuse the model code for training, while layer-wise requires user to rewrite their model definition. And the rewrites are challenging. User-defined GNN models can be complex. And this is an example. For example, we have a 2-layer GCN network, and its forward function is very simple. And to training it, I think most of the developers know how to train this model, and to use the node-wise inference and just reduce the code of training. But to perform layer-wise inference, we need to first enumerate all layers, and then we create an empty tensor, and we initialize the sampler and data loader, and then we enumerate state from the data loader, and then we put them to GPU, and here is our computation, and finally put them to CPU. And we can see this is corresponding to the first 2 lines in the forward function, which means if user want to write a layer-wise inference function, he must need to know how to spell the forward function to several layers. For example, this 2 line is the first layer, and the next 2 line is the next layer. And since node-wise is easy to employ, has a long runtime, and layer-wise is hard to employ but faster. And we can know our target is to build an easy to employ and with a short runtime. So here is our general idea. we can create an automatic layer-wise function with easy-to-use APIs. We can rewrite the training code to layer-wise. And to achieve this target, we will first know why it's hard to employ the layer-wise inference function for the users. First is user need to spell the user-defined GNN model according to each layer, and this may be complicated. And user need to know and understand the design of layer-wise inference runtime. And these two problems, and here is our general idea. For the first question, we can automatically spell the user-defined GNN function. And secondly, we can provide a general inference, a layer-wise inference runtime. By how to spell this, we can introduce a computation graph IR in this. And then is our system design. We built the DGI, automatically translate user-defined GNN models to layer-wise inference programs. And this feature is the oversight design for our DGI system. And you can see the user code here. Here is a GCN function and with a forward function. And how user only need to import the auto inference from DGI, and call the inference function can produce the layer-wise inference. And when DGI notice the GCN model, we will first use a tracer to trace the forward function to a computation graph. And then we will use a splitter to split the computation graph into several layers, which is, we also call it as conv blocks. For example, this is the first conv blocks, and here is the second conv blocks. And then we will recompile it to the Python code. And here is the first conv blocks. You serve the function of these two lines. And here is the second conv blocks. And he served the function of the last two lines in the GCN. And finally, after we generate the functions, we use an inferencer to provide a general runtime for it. And here is our execution data flow. We use CPU for storage. Also, we can use SSD for storage, and we use GPU for computation. And we have three parts. We have three main components in our DGI design. The first one is a tracer. It can convert the Python code to the computation graph. And the second one is a splitter. It split the computation graph to several conv blocks. Finally, it's an inferencer. It provides a layer-wise inference according to the conv block we generated. So it's why we are going to so the tracer target is to obtain the computation graph of the forward function. And here is a computation graph. And so we have many open source IRs and tracing tools can be used, such as TouchFX and TouchScript. And finally, we choose the TouchFX as our implementation since it is built on Python and is easy to use and easy to imply. And compared to TouchFX, TouchScript is a low-level IR, which is it used C++ in language. So we finally designed to use TouchFX. And after tracing, we categorize the operators into two categories. The first is the normal operators like the add, reload, math mount. And these operators only perform actions on tensors. And second is the graph convolution operators such as GCNconv, JTconv, also like SageConv, and so on. And here we tag them to yellow, and the normal operators we tag as white. And then is the splitter. Our target is to split the forward function to several conv blocks. And here we can see the computation graph we generated in the tracer. We split it to two conv blocks. And the problem is how to spell it. and we can just consider the computation graph as a topological graph with 2 types. The first one is graph convolution operators, and the second is the normal operators. And we can use manual defined rules to split the computation graph to several conf blocks. So we set 3 rules for the splitting. The first one is called layer indexing, and second is minimize input, and finally is upstream bounding. And the first rules avoid multi-layer in one conf block, which means we cannot pack conf1 and conf2 into the same layer, and since we only perform one hop neighbors in the layer-wise inference. And the second is to minimize data transfer between conf blocks. We can see if we spell here, and the two data transfer will happen, but if you spell here, only one data transfer will happen. It seems we need to transfer data from CPU to GPU. And finally is inside the conf blocks, we avoid repeat redundant computation. You see, if I split here, the ReLU will perform the computation of output tensor. But if you split here, the ReLU is before the conf block, the conf2, and it have to perform a computation of input nodes, which we also know input node is the neighbor of the output nodes, is larger than output nodes. And then is our inferencer. Our target is organize the splitted conf blocks and perform computation. And we first use a schema to record data movement between each conf blocks, and we provide a general interface for computation. And this is our working flow in our conf block. It's similar with the design of layer-wise inference, but the create input output tensor steps, we can create it according to the schema. And the compute, we can use the function generated by the tracer and splitter. And other is just like how we do in the layer-wise inference, like for each conf blocks, for each batch, present and data preparation, data transfer, and computation. Oh, it seems this should be placed in front of the for each batch. And next I'm going to talk about is our optimizations. We adopt 3 optimizations on DGI. The first is node reorder, and second is dynamic batch size control, and finally is SSD support. A node reorder is an offline optimization. I think many people know what is node reorder, and is widely used in the GNN inference. And after node reordering, the nodes in the batch are closer to each other. It can increase the shared neighbor inside the batch, and we use the simple RCNK algorithm to achieve it. And then is our second optimization, the dynamic batch size control. We notice a phenomenon. The memory consumption among batches are unbalanced. You can see this is the friendlister data sets, especially after node reordering. This is the friendlister data sets after reordering, and the average in degrees distribution are high here, but very small here. So the high degree batches becomes the bottleneck, and these small degree batches do not consume much memory on GPU. So we can figure out the problem is that larger batch size can increase the shared neighbors, but it is difficult to find a best batch size for different configuration, like hardware, what is the GPU memory, and second, like model structure, like GCN GAT. It's obvious that GAT have to consume more memory than GCN. And then is the data set, like which data set we choose, it is sparse or dense. And then it's embedding dimensions, and there's another configuration like the numbers of layers in the computation graph. And we can see this is the feature with different hardware, different model, and different data sets. And the number here are the best batch size we select is different. It's obviously different on different configurations. So we propose we can automatically change the batch size according to current workload. And we use M to represent the expected memory consumption. It usually be the 19% of the total GPU free memory, and MK as the maximum GPU memory allocated in current workload, and NT as the number of batch nodes, and D as the number of batch edges. We compute a ratio R as M divide MK, and for the next batch, we will plus this ratio. Let me just do an example. For example, we have 10 GBs GPU free memory, and we start with 2,000 nodes and 15,000 edges. For the first batch, we sampled 2,000 destination node and 10,000 edges, and it only consumes 48 MBs memory. And for next batch, we can increase these two numbers, and you can see here the edges become the bottleneck here, but the first batch is the nodes become the bottleneck, and it consumed about 1 GB's memory. And then we can continue to increase the number of nodes and number of edges in the batch, and you can see here it consumes about 6 GB's memory and so on. And then is our SSD support. The layer-wise inference need large CPU memory and require high-end service. And why is it? It need to store the DGL graph data sets, and then it need to store the node embedding, especially for the intermediate tensors we generated during the layer-wise inference. You can see that 3-layer GAT on Peiqi's datasets, it requires more than 400 GB CPU's memory. It's very expensive here. So we support to allow storing tensors in SSD. This is employed by NumPy map, and we can also store DGL graph in the SSD in the CSV format. And finally, we generate batch graph on SSD and directly get the batch graph to the CPU. And next part I want to talk about is our evaluation. We use 3 SOTA GNN models, 3 public graph data sets, and 2 different hardware to compute our experiments. And first, the dataset detail. For OGBM product, this is a small data set, and its total size only about 2 GB. And the Friendister and Peiqi's are 2 large data sets, which has more than 15 GBs, and it's obviously the GPUs cannot fit in these 2 data sets. And first is the evaluation time of node-wise inference and DGI. And we only perform this on the OGBM products graph. And here is the GCN, GAT, and JKNet, and it's the first layer, 2 layer, and 3 layer. We can see that with the increase of the layer, the execution time in node-wise are increased proportionally. We can see 1 layer 3 seconds, 2 layer 115 seconds, and 3 layer is 7,000 seconds. But DGIs are linear increasing. It takes 2 seconds, 4 seconds, and 6 seconds. And this even go worse when we're using JKNet. You can see JKNet's 3 layer, we cannot get the output among 10,000 seconds. And next is our effectiveness of node reordering and dynamic batch size control. our baseline selects ST, which is the best batch size in terms of inference speed, and we found this by graph search, and 0.5 ST and 0.25 ST. And next is dynamic. Dynamic means we use dynamic batch size control, but we do not use reordering. And finally is our solution, DGI, with all optimization enables. And this is our evaluation result. You can see in most cases, the we using dynamic batch size control can match the performance of using the best batch size. You see the green bar is always lower than the yellow bar. And after we use dynamic control, if we still use the node reordering, we can outperform the ST and dynamic for about 1.5. And we tested on 3 data sets, 2 hardware and 3 graph neural network models. And then is our micro experience. We use the GC model and the friend-distributed graph. And here is our memory consumption on the friend-distributed graph. And we can see DGI can reach a very high level just as it start, but the ST and reorder are just start very small. And this is we select a best batch size because finally it becomes a very large memory consumption. And the second feature is why our system can have the acceleration is because the data transfer between CPU and GPU are lower, and especially for the DGI is lower than ST for quite a lot. And finally, it's the inference time vs layers. If the increase of the number of layers, our DGI can outperform ST linearly. And next is the inference with the limited CPU memories experience. This is the execution time of DGI on the machine with different configurations. In previously, we only used the M3 and M4, which we think these 2 machines can hold the or data in the CPU's memory. But here we try on two smaller machines, 2 machines with smaller CPU memory, and one is 128 and one is 192. And these 2 machines cannot hold the friend-distributed and papers datasets in the CPU memory, and you have to store the data on SSD, and which we mark them in blood. And we can see this in these 2 configurations. The execution time are quite higher than we use in the CPU memory, but it can work for now. Previously, it cannot work. And finally, is our conclusion. We present the DGI, deep graph inference, a system that automatically converts a UDF GNN model for layer-wise execution. We accelerate model inference by node reordering and dynamic batch size control. We scale GNN on large graphs on cheap machine with the use of SSD. And our experiments show that DGI can outperform node-wise inference, and its optimization are efficient. And that's all of my presentation. Any question? Thank you.
Yeah, any
Thank you.
questions?
Peiqi, I have a question regarding to the dynamic batch size training. I'm wondering what kind of optimizer do you use, and how do you tune the parameters in the optimizer?
You mean the dynamic batch size control?
Yeah.
We only use the linear this is only the linear multiplication according to the maximum GPU memory allocated and expected memory consumption. We only need to multiply these two numbers, and we can limitate our sample graph in these two numbers.
Okay. And because the batch size is like pretty big, so do you use like LARS or any other optimizers during the training?
No, we still not use that.
So you still use the SGD, like the item?
Yeah.
Okay, thank you.
Yeah.
All right, given the interest of time, let's go to our next presenter. Xiao Yun from Nvidia is going to talk to us about cuGraph and DGL integration. And Xiao Yun, you can present this, you can share your screen. Okay, looks good.
Yeah. Let me see. This is weird. Okay.
Yeah, it looks good.
Okay, so let me start. I'm Xiao Yun. I'm from Nvidia. I'm doing the cuGraph plus the DGL integration. Okay. So let me first give a brief introduction about like the graph neural networks. So the original GCN is proposed in 2016. It was a two-layer neural networks. The idea is to gather your neighbors' information to your own, and then for the like classifications. So this one has some like bottleneck issue in the memory. After that, the Stanford researchers proposed a neighborhood sampling method in the graph stage. So the basic idea is like limit the number of neighbors in sampling. So the the memory bottleneck is solved in the graph stage. So here is an example about the workflow of the GNN. First, we have the data, we load the data, and we do some data processing. And after that, we need to define how do we build the graph. It's like graph modeling, and then we go to GNN training and get the result. Oh, this is an example. So basically, for the graph, this is example for the document classification. So basically, they build a graph of words based on the document and then put into the neural networks to get some result. So in GNN computation, the graph sampling and the gathering features can consume 50 to 80% time. So in this workflow, you can see we have the graph structure, and we also have the node features. And then we need to get the subgraph from the sampling. And then we also need to extract the corresponding features from the feature matrix. And then we put them into the graph neural networks for training. So the sampling and gathering, this picture shows it is like consume a lot of time rather than the training. So that gives us some motivation about integrate cuGraph with the DGL. We want to sampling with the cuGraph on the GPU one. And we also want to put our features on GPU as well to avoid the data movement between GPUs and CPUs. So currently cuGraph sampling functions support EagleNet's extraction, uniform neighborhood sampling, node-based subgraph extraction, and random walks, for example, node to act. This is an example for our random walk. You can see with the number of seed nodes and then with the graph goes to deep, our cuGraph scales very well compared with the DGL one. And let's jump into how do we integrate DGL and cuGraph. So this is an example that in the for the node classification for graph stage. So as you can see in the read graph part, we need to change it to from the DGL to cuGraph. We want to build a property graph and then put it into the graph storage and add the node features and edge features to it and edges to it. And then we want to, then in the sampling and training, everything stays the same. So here the neighbor, the data loader will call the neighborhood sampler, and the neighbor sampler will automatically call our cuGraph functions instead of the DGL one. And in the training side, it is also the same. It is also the code will just take care by the training data loader, so we don't need to change anything. So how do we achieve that? On the cuGraph side, we have the cuGraph store, cuFeature store, two classes in the cuGraph library store to store the graph structures and the features of nodes and edges. And there are also some corresponding functions, for example, fetch functions and sampling functions in the classes. And on the DGL side, we also implement the cuGraph storage class in the DGL. So this one will call the functions in the cuGraph class, and it will return the functions types. The functions, the type of the functions will be returned in the DGL side. So you will, so here will automatically like give the data type you want in the DGL. And we also support the integration with the Peiqi. So to support that, we also have some conversion functions between DGL and cuGraph. So we are using the DLPeg this support the zero copy technique to convert the graphs into between the two framework. So from the DGL side to the cuGraph side, we have the two called the two cuGraph functions. So the input is a homogeneous graph in the DGL, and the output will be a cuGraph function. So for example, in this Luan example, we want to get the DGL graph into cuGraph and then change it to an undirected one. And we call the cuGraph functions of Luan to put this one into that one into the function and get a result. Yeah. And from the cuGraph to DGL, we simply also use the from the DLPeg. So these are the source and destination nodes, and it is we put them as a edge list, and then we use the DGL graph to build the to convert it. Yeah, that's all from my side. Any questions?
Hi, yeah, this is Leo. This is awesome to see. I was very curious. So on our ETL pipeline, we're actually coming from Dask cuDF and potentially using GPU Direct all the way from SSD. And so far we don't really use, we'll use cuGraph only for occasional, we'll make a projection and compute something, but we're mostly living on the Dask cuDF. And I'm kind of curious, and we have not used the property graph of cuGraph. We just, again, stick with Dask cuDF, like a node table, edge table. I'm curious if you have any thoughts on how we should be thinking about this project.
So the main, so the main part is, do you want to scale it to like multi GPU for? Do you also put your features on the cuDF Dask, or the features on the CPU?
We're using the Dask for a few reasons. We're using it, sometimes it's because we're bigger than memory, so it's just nicer for bigger than memory. Yeah, we do have our unencoded features there, and then we actually get our encoded features there as well. And then we are interested in multi GPU, but definitely like streaming and bigger than memory. Again, like I think big SSDs.
Okay, so I'm thinking like if you want to use some like graph analytics tools in the cuGraph to pre-compute some like graph analytics metrics, and using that one as a feature to your graph neural networks as an embedding, then you should consider to use our graph storage And also we also have a graph as a service, like Rick will introduce it like later. So yeah, Joe, do you have anything to add?
Hey, this is Tristan. I want to make quick comments. I think I kind of understand what Leo is mentioning now. I don't think it supports now, but that's the direction we're towards to integration. How do we integrate the cuGraph in the future? Having the Dusk at the back end or cuDF, Dusk DF in the back end to support, to make sure the back end can do sampling or provide the feature-wise to the current integration itself. It does not support that, but it will be there in the future.
I'm sorry, I didn't understand what you're saying there.
What I'm saying is like that. What you mentioned is the design change we're trying to make sure that have better integrations between cuGraph and DGI.
Yeah, Leo, ultimately, we want to make it seamless, right? So if you have data in Dask cuDF, you can build a graph or just pass it over to DGL, and that basically doesn't cost you anything. That's where we're headed. Yeah.
Right, and so like, and I saw in the conversion functions, the cuGraph property graph just takes the cuDF series anyway. So presumably, maybe it'll just take a Dask series at some point, something like that.
That's kind of where we're headed. That's right. Yeah.
Yeah, this is Rick. I'm with Nvidia with Xiao Yun and Joe. I was about to chime in and say that as well, because the property graph is basically internally implementing very similar to what you've done with your node table and edge table. And I would imagine that's a pretty easy kind of a seam there with the rest of the software stack where you could kind of hook in at that point.
All right, awesome. Yeah, great to hear.
Yeah, after Rick's talk, it'll be much clearer, I guess. So.
Yeah, I hope so.
So I guess Rick is next. So Rick, you're up. And Rick is going to talk to us about cuGraph, or Graph as a Service overview for large scale graph analytics in GNNs. And
all right, thank you. Am I sharing my screen?
It is coming. It says it's starting. There it goes.
Okay.
We can see it.
Thank you. Yeah, thank you. I'm Rick Ratzel. I work at, as I said, Nvidia with Xiao Yun and Joe on the Rapids team, specifically the graph analytics team. So I'm going to talk today about the Graph as a Service project we've been working on. We're just calling it GAS. I'm going to go over first some of the goals of GAS with respect to GNNs. I'll show some crude block diagrams to go over the high-level architecture. I'll also, excuse me, go over customizing GAS for specific workflows. Talk about some more client-side design patterns that have been kind of evolving as we've been using this, and then talk about some of the upcoming enhancements too. So real quick, some of the overarching goals that we are trying to achieve with GAS is kind of the first one really is to make managing GPU resources for large scale graphs very easy and not too intrusive to the GNN framework itself. You have to basically dedicate multiple GPUs to very large graph data, typically for the duration of the workflow. And ideally, you don't want to have much resource contention there. And using this graph service, we've allowed ourselves to minimize that resource contention and really kind of make the design partition nicely, and it works out well. Furthermore, we want to scale from single GPU to multi-GPU to multi-node multi-GPU without having to change any of the code required to integrate it into the GNN framework. Of course, we want to support multiple concurrent clients or processes and threads sharing the same graph data from the same resources. And a lot of that concurrent programming, the synchronization and batch processing details involved with that, those are all implemented server side. So the client code is simplified quite a bit. And of course, with multi-node, multi-GPU, sometimes the deployment is complicated. One of our other goals is to simplify that. The plan is to have a Docker image in place where all the software is installed and compatible. And then clients use just the same simple GAS client API for both single GPU, multi-GPU, multi-node, talking to this service running in the Docker container. So real quick, this is kind of rough overview of block diagram that kind of demonstrates what a typical multi-GPU deployment would look like. You can see on the left is the client application, and they're just using the thin gas client software. On the right is the gas Docker container. It's going to have all the software required to do all the graph management, graph sampling in a multi-GPU environment, all contained in the container. So this has, in our case, we have a Dask-based infrastructure. It's all set up and working with one worker per GPU. In this case, 4 GPUs are dedicated to the service. And then inside that, we hide or kind of abstract away all the other components required for the application, such as cuGraph, of course, the property graph, which we talked on, cuDF, and all the other APIs to do various sampling and ETL steps. You can see how this extends to, in this case, a multi-node deployment. On the left here now, the client application has access to the entire machine, all 8 GPUs. And on the right, we've dedicated 8 GPUs, the entire machine here to gas and the graph management. And then scaling out further to a multi-node, a larger multi-node deployment, you can see that we can continue scaling to multiple machines within a cluster. And then the client really doesn't have to change anything. The configuration is mostly, for the most part, kind of isolated from them. And they just use the same gas client software to connect and run analytics. One of the other things we noticed, of course, is that a lot of operations, because this is a client server architecture and there's RPC calls involved, we don't want to do a lot of back and forth between client and server. So given the opportunity to do more, I guess in this case, ETL steps in particular, server side, we can do that via these extensions. It's basically like a plug-in mechanism, you can think of it. So this allows all the custom code required for doing ETL and graph, loading the graph data into the GPU memory on the server. These are nice because they also allow multiple clients to access the same basic extension in a very consistent way. So code sharing is done easily. The clients just see another API on the server once these are loaded. One of the design patterns that we've started to establish is the notion of kind of these proxy objects. So on the left is basically the integration that Xiao Yun described, or we call it a local integration. cuGraph is in the graph storage class. It's abstracted away from the rest of the design, but it's still running locally on the GPUs for that machine. This is nice. It's fairly non-intrusive. The application just sees the graph storage instance, which is in a Python kind of duck type manner, similar to any other graph storage implementation using the same APIs. We kind of extend that concept for gas and use a gas graph storage version. And then likewise, it's returning data via a tensor proxy object. Those are basically just, as I said, mimicking the same or providing the same API as the local installations, but internally they're making calls to the gas server. So this is nice because the rest of the client application isn't affected by a local run versus a remote run. You can sort of get an idea of how these might look in code here. On the top there, that's just basically using the gas client API to load some data and then access, get some the vertex data for a particular set of IDs. If I use instead instantiate a tensor proxy, I can do the same thing and I can pass that tensor instance throughout the rest of the DGL code, and it's going to access the tensor just as if it was a all local data. You can use the same array indexing mechanisms and get the same results. Of course, one of the bigger performance improvements we're working on is to allow the server to write results directly to a client's GPU. As you can imagine with a standard RPC, if I want to, I guess, return results to the client without this mechanism, I'm going to have to do a device to host copy, a serialization step, and then transfer it to the client, which is going to basically negate a lot of our performance improvements that cuGraph gives you. With what we're talking about here, we will run nearly probably as fast as a local installation, given the right infrastructure. So this is still in progress, but it's looking promising so far. Another set of enhancements we're working on, I guess, or just features in general, is we want to, of course, provide Conda packages. The nice thing about the client server approach is the server package the client package is very small, very thin. It's really only requires I think NumPy and the RPC package that we're using, and then Python, of course. And then the server, on the other hand, requires cugraph, cuDF, Dask, the RPC package, many other things. But the nice thing is that's all handled on the server side. Clients, and in our case, actually, clients don't even need a GPU if they want to just access graph data via the client API. They can install the thin client. And then the Docker image too is something we're working on still. The nice thing about that is that we can, it should, when we're done, really simplify deployment. Assigning GPUs to the service is just a matter of exposing more GPUs to the Docker instance with the dash GPUs option. For sharing the auto-generated Dask configuration, you would volume out /Dask, and then multiple containers would be able to access that configuration for the Dask bring up. And then similar, volume mounting /logs to access logs from all the workers, and volume mounting /config to specify maybe some non-default config options, hardware configuration specifics and things like that. That's all I had. Like I said, this is I think I mentioned it, this is still a very early work in progress, and it's changing quite a bit. But so far it's been very promising in the initial integration to DGL and Peiqi that we've done so far.
Rick, hi, this is Joe. And how many GPUs are you testing with right now?
Right now, it's only on my workstation with 2, but I think next week I'm planning on running it on a node with 8 GPUs, and then I want to do a multi-node cluster relatively soon. But let me show you the picture. Basically, GAS is really just kind of a wrapper and abstraction on top of what we've already done, as you know, with cuGraph. cuGraph is scaled out to, I think we've demonstrated 2,000 GPUs using basically the same internal infrastructure. What we've done here is kind of wrapped it in a service. So I'm expecting the same performance and results scale-wise that way.
Yeah, great, thank you.
Mm-hmm.
Yeah, maybe just as I was chatting with folks in Slack on this. This actually pretty much mirrors what the Graphistry infrastructure we've been building for over a year. So definitely agree with the direction you're going here.
Excellent, thank you.
Yeah, like I think this is this is a big deal. I'm kind of curious, like when you're doing the Dask for the cuGraph side. How are you keeping the node tables and the edge property tables like partitions? Like, how do you keep that stuff in sync, or balance?
Yeah, right now the multi-GPU support for the property graph, that's the kind of the underlying graph store is basically what we're using internally here. We're using Dask cuDF, and we're pretty much right now, it's very early, we're just throwing it at that and seeing how it works. But I'm imagining we're going to have to do some optimizations kind of along the lines you're talking about.
Yeah, we're definitely trying to figure out what's what are good patterns here. Like there've definitely been Slack discussions on that between us and the Nvidia teams. So I'll be curious how that progresses as well.
Yeah, me too.
But Leo, since it is in Dask cuDF, we could start exposing more kind of basic cuDF features and not just graph functions.
Yeah, I mean, yeah, we actually stay mostly in Dask cuDF because of that.
and Rick didn't get into it, but he has a mechanism where you can define, not quite UDFs, but you can define your own functions that are then callable.
Yeah, like the thing we were talking about Slack, I mean, me and you know, but I guess for other folks here, you can, when you're doing like a map partitions, you can actually have kind of consistency between the node table, node partitions and edge partitions, so that if, like, for example, we're talking, I think, for example, subgraph mining. So if we're working on samples, you can actually have each partition be a sample or a set of samples, and you can make them kind of consistent across partitions.
Yeah, I have another question. So, obviously this is can host fairly large data sets. Have you tried, what are some of the benchmarks or data sets that you've actually tried to run on this?
Right, yeah, right now, fairly small. They fit on 2 GPUs with a little bit of room to spare. But and that right now the bottleneck is because I'm just using a basic RPC, the data transfer. So performance is, I'm still seeing less than a gigabyte a second. But as soon as we start implementing the extensions to use things like UCXPy, so I can get a direct GPU to GPU copy, I'm expecting on my system with NVLink, probably in the 50 gigabyte a second range. Now, as far as the actual like sampling algorithms and things on that, I don't have those benchmarks, but internally they're running at standard, cuGraph GPU speed. I don't know if Xiao Yun or Brad has a benchmark number for that off the top of their head.
Not for the sampling. I mean, for cuGraph, we have run, like Rich said, on 2048 GPUs. We've done 4 trillion edges. Basically, PageRank takes 19 seconds or a little bit less than that. Louvain on really 1.1 trillion directed edges or 2 trillion undirected edges is a little over 5 minutes. We'd like to really, improve those times, but it does show that we can scale to big numbers. And like Rick said, this is just a wrapper on top of cuGraph, so we expect to see the same type of scaling and performance. That was all on an RMAT data set because we didn't want, 40 terabytes of data laying around on disk.
Yep.
Related to that, I was curious, and this could be also for the inferencing speaker at the beginning. We're getting into scenarios where we might have something like a Kafka blog stream or something in front, and then we're getting into doing the inferencing for basically on that. And we are on a full GPU setup, and so what we've been thinking about is like, okay, like, do we have like some sort of like a vector DB in the middle? Do we have we just been trying to figure out, like, for the kind of like a streaming inferencing layer, how to start thinking about that. This could be like, IT logs, web logs, things like that. I don't know if people have experiences or thoughts there, especially with warm working sets.
Any other questions, folks? No? Okay, great. Well, I think we are doing great in terms of time. So we were able to speed through all 3 talks within an hour. So I want to thank everyone for attending, and we'll see everyone next month in August. We'll definitely do a talk on more detailed on what we've released for 0.9 on DGL, and also what we would like to do for 1.0. And until then, I want to thank everyone again for attending, and we'll talk to you next month. Thank you.
Thank you very much.
Yep,
Thank you.
bye.